Can you all see my screen?
Yeah.
Awesome, cool. So we have a new branding actually. So Praetorian is a security company. We find vulnerabilities in products and networks, and we tell our clients how to fix them. So today we're going to be talking about HTTP request smuggling as a kind of grasp for myself. Who all knows what this is? I got no responses. Cool, great. This will be a fun learning experience. Cool. What is it? This we're going to talk about today. How can you actually find it and exploit it? And then we'll be talking about a cool proof of concept, which we have done ourselves, but we're not really going to demo, but we'll do some interactive sessions with it. So what is request smuggling? Well, in normal situations, we have HTTP1 communications, and it's actually common to send multiple requests over a single socket. So if you're connected to a HTTP 1.1 server and you send multiple requests very quickly, there's a good chance that it's just the requests are placed back to back. And then the server just parses the header. Normally it's the content link that will say, all right, this is how many bytes I'm going to read to say this request is over, and then I'll read the next request. And this works fine for most things. There's nothing inherently wrong with this, but it does get confusing when you get to kind of modern services. So what's modern systems actually are composed of multiple parts that all use HTTP. So what we typically see is a load balancer and then some sort of backend service. You can have, in the cloud, you can have Elastic Load Balancer being placed in and then being routed to an EC2 instance, things like that. So they can actually take multiple different requests from users and route them over the same TCP socket. And this can cause problems because what it means is many different people are using the same socket. So the front and the back end servers really have to agree where to parse requests. Otherwise, it can kind of get confused of whose request is who. So normal flow front end, you can think of this as a load balancer, and then your back end, so think of an EC2 instance or something like that. Normal flow, you have user one sending blocks of data of HTTP requests, user two sending blocks, and they get routed correctly. However, the request smuggling is what if user one can actually send requests, which gets parsed with user two's request. So we are going to go after this attack, and it's very exotic. And this is actually was documented all the way back in 2005. But back then, it really didn't have too much of an implication because it wasn't seen in the wild, and it took a little bit to exploit it. I mean, it wasn't until more modern improvements have been made that you're starting to see people really trying to fix this problem. So here is a very quick example. Here we see on the right, there is these post requests with two content links. Normally in a normal HTTP request, you don't have two content links, but in this case we do. And let's say that the front end doesn't really know what to do with this. So it's just going to take the first one and it's going to say, okay, content length is 6. So I'm going to send over 1, 2, 3, 4, 5G. But then the backend server reads this and it only reads the second content length. And it says, oh, there's only 5 bytes in this request. And so you kind of have this orange scenario that's being poisoned and being held in the socket until the next request comes. So under the hood, this front end will forward the blue and orange data. However, the back end will only read that content length 5. And this is a kind of theoretical scenario, not really one that's happening right now. But whenever the next request will come, it will be, the orange will be appended to that socket because it's just back-to-back data packets, and it will cause it to cause unexpected responses. So in this case, it would make a G post, and odds are the server will be like, I don't know what a G post HTTP request is. Like that's not something I support. Any questions about how this could be possible? Because this is really the foundation of this talk.
Could you explain, so like, does it the header just get passed twice in this case, or like where does the second contact length go that allows the attack to happen?
Sure, great question. So this is a theoretical think of smuggling attack. So in this case, we'll say the front end server reads the first content length and saying, oh, this message is 6 bytes. and it'll pass this entire all the way up to this G to the backend server. And then for some reason, the backend server reads this content length and says, okay, there's only 5 bytes in this request, and it's only going to read up to these. So there's nothing specifying that that has to happen that way. This is just like a condition which could cause a smuggling attack if the front end server and the back end server don't agree about what content length header they're using.
Oh, okay. Thank you.
Yep. Yeah. And we're going to get more specific as we go on, but this is kind of the high level overview. Cool. So this is the part that's most interesting. If a message is received with both a transfer encoding header field and a content length header field, the latter must be ignored. So this is in the RFC 2616. If you don't know how web standards are kind of made, so how does a browser operate? These are kind of dictated through these RFC documents, stands for request for comments, and they're kind of detailed of how things should act. And so instead of using content length headers, you can also use transfer encoding. And a common transfer encoding is called chunking. And so I have a little addendum on that. First, I'll go here and then I'll go backwards. So chunked encoding is something that can go with the transfer encoding type. And things like burp, it'll actually automatically be chunked. You don't have to worry about it. But how chunked encoding works is it has a chunk size followed by a new line, followed by the contents of the chunk. And then the message is terminated when you have a chunk size of 0. So what's interesting about that RFC statement? Whenever we find a way to hide this transfer encoding header from one server in a chain, it will fall back to using content length header. And we can desynchronize the whole system. So vice versa, you can also hide the content length header, and then and the server will handle and fall back on the transfer encoding header. And so we can kind of do that to screw up the system to be able to smuggle requests. So here is the next attack. So if you recall, in the first example, we had just had 2 content length headers, and it was kind of which one is going to be parsed by the front end and which one's going to be parsed by the back end. Instead of having 2 content length headers, because that's definitely not going to be supported on most systems, you can just have 2 different headers, one for content length and one for transfer encoding. And so this chunked guy is going to, if you recall, you have the number followed by the number of messages. So this is 6 followed by 0. Or you could have the content length that's blue that would just have space 3. So this would have just a content length of 3 with just this first 6. So if the front end only reads the content length header and it ignores the transfer encoding, it will be passed to the server, and then the server, if it takes the transfer encoding and ignores the content length, it will then cut off and inject and poison with this orange bytes. And so the next time this green request comes in, it'll be appended to this request. This is a little more complex example. Really, the thing that I'm introducing, instead of having 2 content lengths header, I'm just having another type of way that the HTTP tells how long the request is. It's just called chunking, and it's a little bit different syntax. And you have to kind of know how to read these, but just know 6 is how long the chunk is. Here's the chunk, and then here's 0, so the message stops. So any questions how this could get passed to trick the front end and the back end? I'm sure there's some questions on this one.
Yeah, the content length of 3, where does that come from, and what bytes does that cover?
Sure. So this bytes will just cover this. There's an extra space that's invisible right here, but it's going to cover the spaces in 6. So it's only going to cover up to the blue.
Okay.
But good question. I was actually confused about this as well. I would figure the content would be length would be 2, but it says 3. So like either this example's wrong or something's off. But good question. Okay, so what? We can run into these situations. There's actually 2 types of request smuggling in this case. In this case, this is the front end taking in the content length, and this would be the server handling the transfer encoding. So it could be vice versa of which one's messed up. So it could be CLTE. These are just common ways to differentiate the two different attack types. So this means the front end server uses the content link header and the back end server uses the transfer encoding header. Or you have the TECL version where the front end uses the transfer encoding header and the back end uses the content linked header. So if we kind of have this, I wanted to have kind of an open discussion. If an attacker put this in, what would it do? And if someone's confused about what the 9F means, recall this is just how big the chunk is. So this is the hex number that would be how big this chunk is, and then followed by 0, and that ends the message.
So we're hoping that this put request gets like prepended to somebody else's request, right?
Right.
So are we trying to leak the other person's request using our prepended put request to create a new user?
Yep, exactly. So let's say someone's logged in, they have a session, and you are now tricking their request to make a put request, kind of almost like a CSRF, but they aren't even aware of it. And it creates a new member that is ours, named user test ZZZ. Exactly. So this is an example of like, all right, so we have request smuggling. What can we actually do with this stuff? And this is a really cool example because it has impact and the person isn't even aware that they've made the request. It's all done on the back end, and odds are that the original request that the user intended to make, it just isn't going to go through. They'll just have to remake that request. Okay. So that is at a high level what request smuggling is. So how do we find vulnerable servers? So as you saw, the root cause is the front end and the back end not agreeing onto which header they're using. And it's either the front end is using one version and the back end is using a different version, and it can kind of cause these desync issues to handle packets differently. So like all good things for web app hacking, it's almost done in Burp. So I'm assuming that you're familiar with the tool called Burp Suite. It is kind of a production service that does a bunch of HTTP proxy requests, and you can repeat things and try to do active scans. But it also has extensions, and there's one called HTTP Request Smuggler. And it's in the B App Store, so it's just built in, and it's made by Portswigger. So what can you do? If you're listening on the proxy tab and you have a request that you've captured, you can right click on the request and you can do launch smuggle probe. And to actually see what requests are being made, we can also use another extension called flow. And so it'll just show you a list of other requests, and an example success would be a 504. Why a 504 is a good indication that it worked is that if you recall, the first request won't actually finish the socket because the backend hasn't ended the connection yet. And so you'll kind of have this timeout and you're waiting, and it won't return until after the next person makes another request. So you have to make a request, it'll have this kind of timeout session. And if other people are making requests at the same time, there's a good chance it would end and it did get injected. Or if no one else is making any requests at the same time, it'll just time out. Does that make sense why 504 is a good indication as to why it's broken? So once we run that intruder and we figure out that, hey, this server is actually vulnerable to smuggle attacks, we can use another tool called Turbo Intruder. And it actually just comes built in with the HTTP request extension. And this will automate several different attack scenarios to kind of simulate these attacks, and it'll let you show the response to look at it. And so how you do that is you would review example requests that kind of indicate that it does vulnerable to request smuggling, and then you can right click and do smuggle attack. Cool. So going back to the so what are other cool things we can do with this kind of attack? Oh, I got a chat. Is this extension available in the community edition or Burp Suite? You know, I really don't know. If y'all tell me, that is fine. I was going to demo it, so at least y'all can see how I would do it. So that's a great question. If someone else knows, they can answer. And I can go back to the name real fast. Oh, no. It's called just HTTP Request Smuggler in the BFs before. So we saw in that post to Trello, that put request, what are other things that we could do that are bad? Well, another thing you could do is you could cause a redirect. So if you are trying to obtain a JavaScript file, you can redirect it to an attacker controlled JavaScript file. And at that point you have JavaScript that you can run cross-site scripting attacks or things like that of nature. You have the ability to post data to steal information. So if you are trying to somehow get someone's name, if you control where you're sending stuff, you can kind of exfiltrate their request that they were trying to send over to your own attacker controlled website. And you can also smuggle kind of this cross scripting. So you can kind of force it to respond in the server back with JavaScript. So let's say their server responded, say like, hey, this is an unaccepted user agent. Here's the user agent that you put in. You have controlled input there. So all these things are kind of interesting that you can do with this attack smuggling, this request smuggling. And okay, next what I'm going to do, I forgot to put the link. I'm going to go to a Burp Suite lab. And there is, if you aren't familiar with the Portswigger labs, they have a large collection of nice web applications attack you can do. You can log in, so you can make your own free account. And then there's one for HTTP smuggling. And I'm going to stop sharing. And then I think I will just share my screen. Let me make it somewhat safe for a second. Okay, make sure I'm not showing anything. Okay, can y'all see my screen now? Okay, yep. I got some head nods. Awesome. So this is the Portswigger lab. So this is, I've already solved it, but this is HTTP request smuggling, some basic TECL vulnerability. So if you recall, that's the front end using the transfer encoding method, and then the back end using the content link header. And if we go to Burp, I'm just going to create a new project. And I'm going to turn off his intercept. I'm going to refresh. Doesn't like that. Well, let me log in real fast. Let's see if it logs in. There we go. Cool. So I think it just spun up another server for us. So actually nice, because it'll show it's not solved. So we have the server, we have our burp history, and we have the request coming in. So I already have the extension installed. So all I did is I went to Extender, I went to the B App Store, and then I searched for Smuggle, and I was just able to install it. I can't remember if this is Object Community Edition, but this is me using the professional. So once I have that installed, what I'm going to do is right click, and I'm going to do HTTP Request Smuggler and do Smuggle Probe. What this is going to do is going to kick off a lot of different requests. And the way I'm going to kind of view that is using this other extension called Flow. And so this is all the requests that are made by Burp in the backend that I'm not really fully aware of, but it'll be nice to see those scans being happening. So I'm going to Smuggle Probe, and I'm going to go to Flow. Oh, I'm going to leave the attack config the same. So there's all sorts of different ways you can trick the front end and back end to kind of hide the contact length header or the transfer encoding header. I'm not going to go into those, but just know that there's many different tactics, kind of like how there's many different tactics to find SQL injection or things like that. Got a chat item. Okay, I am on community. I can't see it in the App Store. Well, I apologize. I should have checked on that first, but we can at least look at this.
I said I can see it.
But you can see it. I can't read here.
Oh.
So you can see it's kicking off requests, and it's trying a bunch of different stuff, and it's just going. I don't want to wait for it, but just know that eventually this can create a condition that has a timeout. So it would have that 504. What that would mean is it's bypassing the filtering on those headers, and so it is doing that request smuggling. And the way I would typically do it is once it finds the 504, I would right click an example request, and I would do smuggle attack, and I would choose which type of attack I want to do. What this does is it will spin up, and it has code. I think this is some Python code that will go in, make some chunk sizes. It'll do some enumeration on what attack's going to do, and then it's going to make several requests and wait every half second. So we're going to say attack, and then you'll see it. The engine is warming up, and then it's going to keep on making requests over here until it's going. And you can see if you look at the request, it's doing a bunch of different stuff. So here in this example where you have a content length of 11, and then you have this transfer encoding identity, transfer encoding chunked, and it's just trying a bunch of different permutations that will go and attack this server. In this case, this particular kind of template isn't being ejected, but just know that these tools are just useful to create these attacks and figure out this in a more planned way instead of doing everything manually. However, it's still useful to know how to do it manually. And so what I'm going to do right now is I think I may or may not have it. Got a 500 at some point. What I'm going to do is cheat and then just solve it, because I didn't feel like doing this manually. So if you go to the Portswigger Labs, no, this is and have a solution. And so all I'm really doing is I'm just not waiting for this to finish. So if you recall, I'm waiting for a 504 to time out. And then once I can do that, I can use it to make the request twice. Let me refresh, make sure I didn't actually accidentally solve it. No, I haven't solved it yet. So here would be an example request they would send. So if I, let's say I repeat this, send to repeater, and then I'm going to set my requests to a and so this first request will time out because it's being chunked. And then the next request will activate it'll hit it, and then I'll send it again. Get another request. And I'm not getting the output that I would expect. I'm waiting for it to return like, hey, I don't know what kind of request you're sending. This is the joys of live demos. Okay, that does not work. Go here. That's the solution for CLCT. Oh, well, thank you. Thank you. I am using the wrong one. Oh, sorry. Okay, yeah, so this makes a little more sense. This is a little bit different. Thank you for pointing that out. This is the problem with me using other people's stuff. So send this request. It's going to time out, and then it will wait, and we'll have to send it twice. Oh, dang it. I know I did wrong. So this is also annoying. If you see here, the content length is now 101. It was automatically set. So this is actually an important step. What you have to do is you need to set your settings. So I don't know if y'all can see the top of my screen. I think y'all can, but you have to uncheck the update content length flag right here. Because automatically Burp will be smart and it'll automatically set the content length, but you can do it manually if you undo it yourself, and that's supposed to be a content length of 4. So put 4. And there's a read timeout. Well, this worked earlier. Following the file 0, I need 2 returns. This makes more sense. There we go. This is first request, and then we need to send, but we have not solved right here, and I'm going to send it twice. And then it'll say unrecognized method gpost. Boom, we got it. Sorry that took so long. I did demo this before, but obviously took me longer this time. So any questions about what we just did? So just to recap, the first request, we did a post. And so we set the content length to 4 and the transfer encoding is the chunk. And this problem is the front end is going to use the transfer encoding method, and the back end is going to use the content length method. And so it's going to set the G post for the next request, and it got triggered in this one saying, hey, it's going to do this G post now, and it doesn't realize what just happened. So boom, we got attack request smuggling. I think if we send this again, it'll say we solved it. So that is the solve lab. And I did cheat to do that, but the tools, so to kind of double down again, the first thing is you can use the intruder to find 504s, and then you can use those tools to help automate attacks like that. Okay, and I'm going back to the PowerPoint. Can you now see my screen?
Yes.
Yep. Cool. Awesome. So now this is a kind of proof of concept that we did here at Praetorian, and we thought it was pretty cool. So the Acme challenge is one of the challenges for Let's Encrypt, and you can use it for other vendors to essentially prove that you own the server that you are requesting a certificate for. So here is the typical challenge. You have you give a client, and it gives you a token, and then you host a token on your server. So this file has kind of the thumbprint for your key. And so once it finds that token, it now validates, hey, you actually own this server. And the kind of security of it relies on DNS to trust that it routes to the correct IP. And so one of the interesting things that was right here is that the implementation for Let's Encrypt actually will follow redirects, and it'll redirect up to 10 directs deep. And it can only be done on port 80. So if you recall back on first attacker goals, what if we can do a redirect attack to point it to attacker controlled domain for another server, and we can get a cert without owning the server. So here's the idea. We use request smuggling to influence the Acme verifiers. We redirect that token to an attacker controlled domain. So forcing a redirect. This is just an example server. This is something that we actually use for our VPN services pre-tunnel, but you can see right here that it has the ability to redirect. So it'll grab the host, and then it'll do an HTTP redirect for that host string. And so here in an example request, if you do a post to host attacker, and it will then move it to the location. So it's just an open redirect that is kind of a useful gadget for the goal of getting the certificate we want. So here is the actual challenge that we'll be sending. So what we're trying to do is we are able to post to attacker.com, and then the next request that will be sent by the verifier. So this is Let's Encrypt's verifier. Will say, hey, I want to get well-known Acme challenge.com. But since we're sending it to a pre-tunnel, so this Juno Praetorian Labs is a pre-tunnel server. And so it'll do a redirect to this attacker.com for this verifier. And so this redirect will allow us to control the response for a particular host. So we'll get the move permanently to attacker.com, and then we can give it the token. So because we can do that, we can spin up a certbot. Certbot is a useful command line tool to do the Acme challenge. You can use it for Let's Encrypt. So in this case, we have it doing preferred challenges to HTTP, so it's doing for 80, and we're doing it for the host RSLF-LC. And then we start it, and then we also run our own request smuggling attacks at the exact same time. So it takes a few times because there has to be 3 out of 4 verifiers that succeed successfully. So you have to keep on injecting and smuggling these requests. And after running a few times, Praetorian was actually able to get a certificate for the host that it wanted to. So this is kind of what it looked like internally. It would do a post to this GitHub account. And so this was just an S3 bucket that had the token that it wanted to be hosted on. The location was for this RSLFLC. It would be redirected correctly to get the challenge that Let's Encrypt wanted. And after that was done, we were able to get the RSLC certificate signed by Let's Encrypt, and then we could use it to host our own websites. And so that was a successful kind of proof of concept that we tried. So what this really means, oh, sorry, did someone say something? Nope. Okay. What this means is that if a server is vulnerable to request smuggling, and you can get a Let's Encrypt certificate for that server. And so you can use that and then trick users to go to your website, and they think you're their trusted account because you have the right certificate, and a lot of bad things can happen after that. So any questions about this proof of concept?
So this was a vulnerability in oh wait. So Let's Encrypt has an HTTP endpoint that you need to request from the domain name.
No.
Wait,
So
I'm sorry, I don't
Yeah.
understand how the challenge system works.
Yeah. Let's go back. Let's go through
Yeah.
this again. So how the challenge works is you say, hey, Let's Encrypt, I want to please give me a certificate. And they're like, okay, cool. If you can prove that you say who you are. So it'll give you a token, and it'll try to go to the domain that you gave it saying, hey, Let's Encrypt, give me a token for this domain. And it will do a verifier request to that server endpoints. So it'll expect your server to be hosting this .well-known acmechallenge.token file. And so in this search bot case, what we're doing is we're saying, hey, Let's Encrypt, give me a cert for the the RSLFLC server, but we actually aren't on that server and we're not hosting that file correctly. Does that make sense?
Yeah.
And so what's happening is we're redirecting. We're saying, hey, here is the host that it wants, and we're smuggling the Let's Encrypt's verifier requests. And what we're doing is we're posting it to our actual GitHub. It's being moved to that request, and then we get the well-known request from our box, so our S3 bucket or GitHub file, and it will verify that token matched with the original certbot request that we made.
So we're tricking the certbot when it requests this token from the vulnerable server. We're redirecting it to our S3 bucket, so it gets that instead.
Yes, we're tricking. The request that we're smuggling is Let's Encrypt's verifiers, and because the RSLFLC is vulnerable to request smuggling, we're able to redirect them to our controlled location.
Okay.
But because it's request smuggling, the verifier has it's none the wiser. It has no idea that it's no longer talking to the right server. It just assumes that its request worked.
Okay.
But this was a really cool proof of concept that we did, and it can be very impactful for systems and clients that we interact with. And that is it. That is oh, I got here. You had a question for me?
So the previous thing you showed, so just to clarify, what's happening is that it's jumping to like the correct site, it's validating it, but then once it's validated, then it's jumping to your attacker site, and it still thinks it's on that site.
Yes, exactly. Cool. Any other questions? I know some of this was a little choppy, but a lot of like when this was first released, I think back in 2018, Go was very quick to fix it. So like the de facto AWS Elastic Load Balancer with a Golang server was vulnerable to this attack. And very quickly, Go updated their service to not be vulnerable to these attacks. But for a few weeks, it was a big thing in the news, and then quickly kind of shut down. So we don't see it as much, but it is still available if people aren't updating their servers or load balancers.
I have a question.
Yeah.
So how do you know the verifier request will come in right behind the smuggled content?
Great question. You don't. In this case, it was easier because we controlled the environment. So we controlled the RSLF LC server and we knew it was vulnerable. But in a real world scenario, if it's a popular website, like there's, can be thousands of requests at the same time. So you have to be very particular of when you're sending a request, and it's really just flooding the server and the network for your own kind of smuggled requests and hoping that the verifier request is the next request that gets put into the socket stream. Cool. Well, I've enjoyed talking. I can also ask any questions about Praetorian, about the work we do, and anything of that nature.